Hello everyone. In today's video I will be introducing a new topic called influence line diagram, and it can be represented as ILD. Okay, so now influence line represent the changing value of reaction, shear force or bending moment due to the change in position of load. So I'll write down here, it represent the changing value of reaction, shear force or bending moment due to the change in position of load, loads. Okay, so what does this mean? Suppose for an example I'll explain you by taking an example. So this is a road or it can be a bridge. Okay, and in this bridge what happened, this vehicle is moving. So here what happened, suppose this is a point A and B starting and the ending point. So due to this vehicle at this position, what will be the effect on the road or a bridge? Okay, so suppose the effect will be different when the vehicle will be here, and when we move this vehicle this side, then again the effect will be different. So here also if we move this same vehicle here, then the effect will also be different. So now here, that's why it says that it represent the changing value of reaction as well as shear force and bending moment due to the changing in position of the load. This is the load, right? So now I'll solve a problem based on influence line diagram for a simply supported beam. Okay, I'll write directly ILD, that's nothing but the influence line diagram for a simply supported beam. Okay, let's try to understand this. Okay, this is the most important basic related to influence line diagram. Now here I'll draw a simply supported beam. So this is a simply supported beam where one end is hinge and the other one is roller, and here one point load is acting of 1 kilonewton, suppose. Okay, of 1 kilonewton. Now let's take this as A and this as B. So and this is the L is the total length of this beam. So here we'll assume that the distance from this end to this point load is x. Okay, if it's x, then what will be the distance from here to here? It will be L minus x, right? So now we have to find the reaction, that is RA and RB. Okay, so first if we take summation of all the moment about A, it will be 0, right? So now what we'll do, see, moment summation of all the moment about A, then all the force will move towards A, that means RB will be upward, that means it's a minus sign, minus RB, and what is one load is there, right? And it's acting downwards, then it will be positive plus Oh, sorry, I'm so sorry. Okay, I forgot to take the distance. Yeah, so here this RB, and to reach at this point, how much distance it take is L distance, right? So here RB into L, and always remember, okay, to find the moment is load, L is load into distance. These things you have to remember, huh? So now here load is nothing but this is the load RB, and into how much distance is covered to reach at A, that is L. Now again one load is there, that is 1, and it's acting downwards, then it will be a positive 1 into the distance to reach at A point, it's X, right? X is equal to 0. Now simplify it, then we'll get the value RB is equal to X by L, right? So we have a value of RB now. Now next is to find the RA value. So here to find the RA value, what we know that summation of all the forces, vertical forces, is equal to 0. So here vertical forces summation of, so what, sum of all the upward forces is equal to sum of all the downward forces. Okay, this was the condition in case of vertical forces. Now sum of all the upward forces, sum of, that is only this RA and RB is the only upward forces, right? So here write RA plus RB is equal to sum of all the downward forces is only 1. This force is only acting downward, that is 1. So here now we have a value for RB, so just we need to put the value of RB in this equation. Okay, so here RA plus RB is X by L is equal to 1. So from this equation we can get the value of RA. RA is equal to 1. If it will go that side, then it will be a minus X by L, right? So this is the equation of RA. Now we have a value for RA and RB. Now we can find the ILD for support reaction. So here I'll write ILD, influence line diagram for support reaction. Okay, so here I'll draw the diagram. Okay, so it was like this, and here one hinge, and here is roller, and 1.5 kilonewton X, and the whole distance is L. It was L minus X, right? A and B. Now ILD for support reaction, we have to find the boundary condition now. So boundary condition. Okay, so we'll consider, say, when this unit load, this is a unit load. Okay, when this unit load it is at this point, if suppose is at this point, then what will be the value of X here? So I'll write down here, when the unit load is at A point. Okay, when this load is at this point, then the value of X will be 0, right? So if X is 0, then what will be the value of RB? RB was what? This is X by L, right? X by L. So just we need to put the value of X here, that is 0 by L, it will be 0. So in this condition, when the value of X will be 0, the RB value will also be 0. Now again we have to move this load at this B point. Okay, so I'll write here, when unit load is at B point. Okay, now we are shifting this load at this point. Then the value of X will be this whole L, right? L. Then the RV value will be it was X by L, right? So here in place of X we'll put L. L by L, it will be cut, that means 1 is equal to 1. That means if the X value is L, then RV value will be 1. Now we'll draw this. So how to draw this one? This is A and B point. So here in the first condition, when the value of this one, when the unit load is at A, then the X will be 0 and RB value will also be 0, right? But in the next condition, when the unit load is at B, the length will be X and RB value will be 1 positive, right? So it will be somewhere here. So you have to join this both. Okay, so this is the IL for influence line diagram for RB. Okay, this figure is the influence line diagram for RB. Now you have to find for the RA value. So again we'll apply a boundary condition, okay, for RA value. Now what we'll write, when, okay, the same thing, when this unit load is at A, then now we are finding for RA. So X will be, obviously it will be 0, right? 0. Then RA value will be, this is the equation for RA, right? 1 minus X by L. 1 minus X by L. So we just need to put the value of X here, and it will be 1 minus 0 by L. So 0 by L will be 0 only. So the value of RA will be 1 in this case. Now again we have to shift the unit load at B. So when unit load is at B, then the value of X will be L. So due to this L, the RA, we have to apply this was the RA value, right? Equation. So just we need to put X value in this equation. It will be 1 minus L by L. So this one and this one will get cancelled. It will be 1 minus 1, it will be 0. Now again we have to draw the ILD for RA. So this is a A and B point. Now in this boundary condition, what it says that when X is equal to 0, when the load is acting at A, right? So X will be 0, RA value will be 1. So RA value will go upward. But in the second condition, when the X value is L, then RA value will be 0. You're right. So the IL diagram for RA will be like this. So you can write here, this is the ILD, influence line diagram for RA. Okay. Now these both are positive, right? Just write it positive. Now next we'll find for ILD for shear force at a given point. Okay, so here now what we'll do, we'll redraw the diagram. Okay, so okay, and this is now this point is A and this point is B. So we have a value for RA and RB. RA was X by L and RB is 1 minus X by L. Okay, so here, and the whole length, this length is L. Now what we'll do, we'll consider one point here. Okay, let it be C point. So we are finding the shear force for this particular point, that is C. Okay, so now what we do, it's for the case 1. Okay, so now here we'll assume that the unit load is between A and C. Okay, so here I'll write when unit load is between A and C, it will be somewhere here. Okay, so then what will happen, we have to find the shear force, right? Shear force at this point C. So now shear force at C for case 1 will be what? It will be RB only, right? RB and C. For the shear force, if it's acting upward, then it will be a negative. Okay, so now for the case 2, when unit load is between C and B. Okay, then suppose here the unit load is acting somewhere here, then the shear force at C, then the shear force at C will be what? If this unit load is acting somewhere here, then the shear force will be RA, positive RA, right? So now we'll draw the shear force diagram for case 1 and case 2. Okay, for case 1, what it says that when this was the section, right? This one. So this is the section A. To this one. Okay. This is the one. Let it be A and B. This one A and B, and this point is C. Now for the case 1, what it says that at shear force at C, when the load is in between A and C, right? A and C, that means minus RB at point, minus RB, then minus RB at this point will go downwards, and it was for A and C. So just join like this. Okay, okay, so this is for the case 1. Okay, now we have to draw for the case 2. Okay, so here it was A and B, and this point is C. Now for the case 2, in between SFC, shear force at this point is positive RA. RA is positive, it will be somewhere here. This is RB, right? So here it will be RA. So in between B and C, so join like this. So this one is negative and this one is positive. Now we have to wait. This is for the case 2. Now we have to draw the combined diagram. Okay, so combined diagram will be like this. Okay, so here it will be like this. At point C, one was positive and one was negative, right? And this is A, B, and this one is C. So now here we have to combine this positive and negative. Negative is like this, right? This one negative, and the positive is at this particular point. Positive will be like this. So it's a positive. This is the combined diagram, and this is the final diagram also for shear force. Okay, so now next is ILD for bending moment. Okay, and for bending moment also we have to find for the point C. Okay, point C. So here now again I will redraw the diagram here. So this was the A and B point, and one load is acting on the RA and RB. So here this is RA and this one is RB. Now here assume it as point C, right? And here we are assuming that the unit load is at distance x. Okay, this distance at x. So the distance from here to here will be, the whole distance was L, right? So it will be L minus x, right? Now we don't have the distance from this A to C, right? So here A to C, we'll consider it as A. Then from C to B will be L minus A, right? So now we'll consider, I'll write down here. Okay, consider unit load at a distance of x. Okay, now we'll find for the case 1. For the case 1 here I'll write down when the unit load, this unit load is between A and C. Okay, and again in the case 2, what happened when the unit load is between B and C. These are the two cases which we have to solve. Now we'll go for the case 1. Okay, so I'll write here for the case 1. Now here what it says that when the unit load, this is the unit load. Okay, so here this unit load first is acting in between A and C. So here what will happen, the bending moment, the bending moment, I'll write like this, bending moment at C, okay, is equal to at C, at this point when this load is acting in between A and C, what will happen, this one will be RB into, we have to take the distance till here, okay, RB, and for the bending moment upward forces will considered as positive, right? So here it will be positive RB into the distance, and we are finding for the C point, so it will be, C point is L minus A, right, this one, so L minus A. So we know the value for RB is nothing but x by L, right, x by L, and RA was 1 minus x by L. Okay, so here I'll put the value of RB, that is x by L into L minus A. So here we'll keep the x that side, then it will be L minus A by L into x, then the equation becomes here L minus A by L into x. Okay, now we'll apply a boundary condition here. Now apply a boundary condition. Boundary condition for case 1. Okay, so now here, when the unit load here, when the unit load is at A, okay, that means this unit load will shift at A, this point. Okay, then what will happen? The value of X will be 0, right? And the bending moment at C will be, we have an equation right here, this one. So just write the equation, L minus A by L into X. For this one is not L, it will be 1, right? It will be 1. This is 1. Okay, so this is the equation. Now we have to put the value of X in this equation. Then 1 minus A by L, it will be like this, into X into 0. If we multiply with 0, then whole terms will becomes 0. So bending moment at C for this condition, it will be 0, right? Now again what we'll do, when the unit load is at C, when the unit load is at C point. So now what we'll do, we'll shift this unit load at this C point. Okay, this C point. So the value of X will be, see, up to this point the distance is A, right? So the value of X will be A. Now we have the equation for bending moment at C for case 1 is equal to 1 minus A by L into X, right? So the equation will be 1 minus A by L will be like this. In place of X we have to put A. So this is the equation for case 1. Okay, now again we have to apply a boundary condition for case 2. Now again same thing we have to follow. When unit load is between B and C, right? This was the case 2. So here we have to make the equation first. So in this case the bending moment at C will be, C, the unit load is between B and C. Okay, I'll redraw the diagram here. This was our, okay, RA, RB, and this is A point, B point, and this is C. Okay, so now what it says that when the unit load is between B and C, in between this one, okay, somewhere here. Okay, so what will happen? So bending moment at C, we have to find the bending moment at C. So RA, this one, this is RA, right? RA into, up to here the distance was A, right? So it will be RA into A, and we know the equation for RA, that is 1 minus X by L, right, into this A will come here. So this is the equation for BMC for the case 2 condition. Now we have to apply a boundary condition for case 2. So now when unit load is at B, now here we'll consider that the unit load is at B, then the value of X will be the whole length, right? This is the whole length L, so the X value will be L. So the bending moment at C will be, we have the equation here, that is 1 minus X by L into A. So in place of X we need to put L, 1 minus L by L into A, right? So this and this will get cancelled. 1 minus 1, it will be 0. 0 into A will be 0, right? So now again the boundary condition when the unit load is at C, right? When the unit load is at C. Okay, now we will consider that the unit load is acting here at C. Then the value of x will be up to here is A, right? So the x value is A. Then the bending moment at C will be, what was the equation? This 1 minus x by L into A. So just we need to put the x value in this equation, then it will be 1 minus A by L into A. Okay, so this is the equation. Now this is the bending moment. Now we have to draw the ILD for bending moment at C. Okay, I'll draw here. So this was the, this point is A, this point is B, and C point was somewhere here. Now bending moment from A to C is, for the first condition, A to C is this one, right? This 1 minus A by L into A. It will be positive somewhere here. That is 1 minus A by L into A, right? So A. Okay. So from here also, for the second case, BMC will be, the equation is same. At bending moment at C is 1 minus A by L. So for B to C also it will be same like this, right? And it's a positive. So now you can write like this. This is the ILD diagram for bending moment at C. Okay, so this was all about the influence line diagram, and in my next video I will be solving a problem based on simply supported beam by using the influence line diagram. Okay, thank you.